Welcome back to the classroom. My name is Mr. Wong, and today we'll be covering corrosion reactions. Alright, so for today's lesson intention, we're going to define what corrosion reactions are, and we're going to identify conditions that accelerate it. As part of your success criteria for this lesson, we are going to try and describe the environmental conditions that will allow for corrosion reactions to occur. Let's firstly define what corrosion reactions are. A corrosion reaction involves metal, usually, reacting with oxygen under humid or what we call high moisture, high water content conditions to produce metal oxides. Now this is a standard equation or word equation to describe metal plus oxygen, and then you get the metal oxide. You can see how water here is written like so. It's to say it acts as the catalyst, so it allows for the conditions for this reaction to occur faster. Now sometimes they will have, you'll see textbooks also have this equation where we have metal plus oxygen plus potentially water. So water is part of the reaction and you get a metal hydroxide instead. Now in most questions they will tell you which one they're discussing, but that's kind of the two types of corrosion reactions that can potentially occur. You can see this in lots of different areas, so particularly bridges that cross over water, which have really high moisture content, and then obviously you see also this kind of rusting content here. So that's corrosion for you. It's something you see everywhere, every day kind of a thing there. Now, when we talk about corrosion, you can see here, just a little animation to show what's actually happening. So in the previous slide, we talked about how corrosion is the combination of a metal plus oxygen combining together. So you can see this sort of layers of stuff adding onto it. That's actually the oxygen adding itself onto the piece of metal. Now corrosion is a very slow reaction. There is another type of reaction that involves metal and oxygen, and you would know that as combustion. So it's following through a similar type of reaction, but combustion reactions occur very quickly and release a lot of energy in a very short period of time, whereas corrosion is a very long process that releases energy after a long period of time. So this is actually how you can actually see corrosion forming at the time. What you can see also is over time, if the layers on top are covered by oxide layers, it becomes a little bit more difficult for additional layers to add on. One of the terms people might confuse themselves with is corrosion and rusting. Okay, so they represent actually two different things. Corrosion in iron is what we call rusting. So rusting is a type of corrosion, but it doesn't represent all types of corrosion. It only represents corrosion in iron metal. So what's actually happening here is iron will combine with oxygen to form iron 3 oxide. Water has to be present for corrosion to occur, as we talked about before. Iron oxide is really easy to distinguish because it has this orange-red color. Okay, this is the formula to represent the reaction, and you can sort of see the chemical equation in the center here. So that's our chemical equation, and up here is our word equation. You can sort of see the difference already between the two and why we want to write chemical equations, because it actually tells us what's the ratio of atoms required for this reaction to occur. So to make this iron 3 oxide, we actually need 4 irons, 6 oxygens in total, and then that'll give us 2 iron oxide molecules. Okay, so there's that. Now for those of you who might wonder, how do I write this chemical formula based on this equation here, just remember iron 3 represents Fe3+, Fe meaning iron, and then oxide is 2-. Remember, you always use the crisscross method. You get rid of the positive and negative signs, and so that's why the 2 is there and the 3 is there. They're simply just crossed over with each other. If we look at some examples of rusting, like we said, iron oxide, when it rusts, will have this orange-red color. So that's what you see, that sort of fine powder. Copper, when it forms copper oxide, or when it corrodes, has this sort of grayish green color to it. How do we increase rusting speed? If you have a look here, we have an abandoned ship. This would indicate it was made of an iron frame structure, because as you can see, there's sort of this orange-red color to it. Now, if you see any of those films where ships are under the ocean, they have quite a bit of rusting. One reason is because there's a high moisture content, so that's one, but also because there's a lot of salt water. Now, what's actually happening here, having a high salt water content actually increases the iron exposure, and it also allows for more ions to attach itself onto the metal, causing this corrosion process to go on much faster. So these are sort of the two things you want if you want to increase rusting: high contents of salt in water and a high moisture exposure, essentially just having a lot of water. And obviously in that case, also, there must be a presence of oxygen gas dissolved in that water. Let's have a look at two different types of corrosions. One will be aluminium, but this one is iron. So we said that with iron, it forms this sort of orange-red color texture here. So you can sort of see that here. Now, one of the issues with iron rusting and why it's such a big issue is the fact that when it rusts, it causes flaking effect. So you can see all these little flakes here. Okay, that's from the iron oxide. The issue with this is because it's this sort of flaky structure, it actually opens up pores for more additional water and oxygen molecules to go further inside into the piece of metal, and you don't want that. If the water and oxygen can be exposed to other deeper parts of the metal, it means that the inner parts can also become more rusted over a period of time. Another issue is rusting will thin out the piece of metal. As you can see here, it's thin out this piece of metal because what's actually happening is the iron content is bonded with the oxygen. That causes it to flake, and over time, because it's flaky, it'll, dissipate away from the piece of metal. So that's why we also say corrosion or rusting is almost eating the metal away, because it's actually causing it to lose mass by removing it from the actual piece of metal. Now let's have a look at aluminium oxide, and you can already see there's a massive difference in terms of the structure. Aluminium doesn't flake, or at least it won't cause a oxide layer to become flaky. As a consequence, once it has formed that oxide layer, oxygen can't enter, water moisture content can't enter, so you won't see, so there is no additional corrosion that will occur inside the piece of metal. Okay, so that's what we have there. and as also the aluminium oxide binds itself really closely with the aluminium metal. Again, as we said, that prevents water and oxygen from going through into the metal, causing more rusting. Okay, so let's have a look at the ideal conditions for corrosion. In order for corrosion to occur, we already said that you need water exposure and oxygen, and added, as we said before, we want also a high salt concentration in that water as well. So that's like an additional component. Another thing we want is we want a active or reactive metal. So a metal that is readily able to give electrons away. If you actually look at the corrosion table, it gives you a nice idea of particular metals that will corrode and metals that won't be as corrosive. So magnesium is very active. It is going to be very corrosive. So, or it will be easily corroded, so to say. Zinc, also more corrosive than aluminium. And then we have iron. Now you can see, although aluminium is more corrosive than iron, iron rusting is worse, just based on the fact that once it starts corroding, there's additional exposure sites in the piece of metal, and then that will cause it have a chain effect of corrosion. You have steel, which is a form of iron alloyed, and then you have stainless steel, which is this one up here, which is a multiple complexion of different metals that make it really difficult to corrode the piece of metal. Now gold, you can see, is one of the least active metals in the world, which is also why it's quite highly sought after, besides the fact of its color and its shininess. But because it doesn't corrode easily, you can make jewelry out of it, you can make currency out of it. That's kind of why gold is a really lucrative thing throughout history, or throughout human history. Okay, let's go through this question, the corrosion of aluminium and iron. So based on our understanding of knowledge of the active series, which metal, iron or aluminium, will react with air and water more rapidly? So based on the chart or the table we had from the previous slide, aluminium is the more reactive metal. Okay. Question B, it says iron continues to rust whereas aluminium stops corroding. Explain why this happens. Now, explain is an example of a cause and effect. So what I want to show is the ability to demonstrate why is it like this, why once we form that oxide layer, nothing goes through, whilst for iron, it does. So let's try and explain through it. And our cause, okay, our cause is because iron oxide is flaky. Okay, the reason why this is an issue is because by it being flaky, it exposes many little holes throughout the metal where the moisture content and the oxygen content can then go further inside the piece of metal and causing it to corrode longer. Okay. So the effect that we're looking at here is a prolonged corrosion of the piece of metal. Okay, now obviously this is an issue if we need iron in our infrastructure, or if we need aluminium in our everyday tools. We can't have them corroding all the time, so we need to come up with a method to prevent corrosion, and there are some really clever ways of doing it. But before we go into that, let me just show you this image of some real life examples where corrosion can occur and may not occur. Now the Statue of Liberty, you recognize the color, this grayish color. It's actually made out of copper. Now you know that copper is sort of the brownish red color. So originally what would be the Statue of Liberty, it would look sort of like this. But it looks more like this now. And the reason being is because it's gone through rusting, it's gone through corrosion over an extended period of time to give you this color. So that's an example of a famous monument corroding. For those of you who've ever driven a car or are intending to drive a car, you might find some little spots or patches on the car where the paint has faded. Now the key point when that happens is you must ensure you paint over the corroded parts or you scrape it off. But you must ensure that there is no continuous exposure to these corroded spots, because as we said before, the longer you expose the corroded iron, the more corrosion it will get, and it will just break the frame of your car. So if you see any spots where the paint has gone off, you need to cover it up again. In certain places, I think this was in Northern California, they can actually park their planes outside. Now, in most other places, particularly in Sydney Airport, they would actually park their planes inside a shutter where there's low exposure to moisture, like so and so. But in California, because it is pretty dry or very dry most times of the year, you can actually park the planes outside, and you won't see any corrosion because there's just not enough moisture to react with the planes. As also to note is they also have been painted, so that also can help prevent that corrosion. Another technique of protecting the corrosion is a process called galvanizing. So this process is where you put a more reactive metal on top of the less reactive metal. So say, for example, I want to protect the structure that has iron in it. Okay, if I look at the corrosion table, I am going to put a zinc layer on top of the iron, and this zinc layer acts like a sacrificial lamb, or sacrificial object, and protects the iron below. So instead, the water and oxygen is going to react with the zinc first before it reacts with the iron, even if the iron, some part of it is still exposed. So long as you have some little layers of zinc over it, the oxygen and water is going to react with that first. So you can sort of see it as this process of galvanizing. In the way that they actually cause galvanizing to occur is through this little process that you can see here. You don't really need to understand what's going on here. This is a bit more of an extension part, but the idea is the more reactive metal, in that case example we talked about, which was zinc, it will transfer its ions over to the less reactive metal, and that's how you actually can coat the less reactive metal with a more reactive metal on top. So there's that. Okay, so let's just summarize a couple of methods in which we can use galvanization, and that will be the end of our lesson. So one method is painting, and that's usually used for cars. The advantage of it is it's really cheap and easy to apply. Disadvantage is obviously it's quite easy to scrape paint off, scrap it, particularly if you do little corner turns and you kind of scrape a little paint off accidentally as you make a bad turn. That's something that can happen. You might see in mechanical hardware particularly in the old steam trains, that they have greasy or oil layers on top, designed to lubricate the parts that are, you know, a bit rusty, but obviously it's quite messy and you need to replace it quite regularly. Plastic coating. Now, if you wash dishes at home or when you're drying out the dishes, you might find that your dish rack is usually a plastic coating, usually a metal coating. The reason why is if you have a metal coating dish rack and you expose it to moisture all the time, you're bound to make it corrode. So usually plastic is a better way to go if you want to avoid that corrosion. Might not look as nice, but helps. So obviously if there are cracks in the plastic, it can enter your thing. So plastic can deteriorate as well, so that might not be the best way, but you know, if you don't want corroding dish racks, that might be a way to go about it. You have a thing called tin plating, so this is an example of galvanization, and they actually put tin in food cans. So most food cans are made out of aluminium, or drink cans are at the very least, but they might put tin layer on top of it to prevent corrosion. Doesn't affect the quality of the food, but you do need to use the process of galvanizing electrolysis, which is quite expensive. So that concludes our lesson for today about corrosion reactions. Hopefully you found it useful. If you did, please give it a like and support for future videos to be made, and enjoy the rest of your day.